Welcome back, students. In the previous episode, we studied the electric field in great detail. But remember this, nature prefers energy over force. Understanding potential makes the chapter not only easier, but deeper and more elegant. Electric potential at a point is the work done per unit charge in bringing a test charge from infinity to that point without acceleration. Potential is not a force. It is not a vector. It is simply the energy landscape of the electric field. Think of potential as the height in a gravitational field. Electric field is like the slope. Potential tells you where you are. The field tells you how strongly you will roll. Students often ask, why do we always say work from infinity? Infinity is the point where interaction energy tends to zero. It simplifies mathematics. Any other reference point is allowed. But infinity gives universal consistency. Let us derive, not memorize. Electric field due to charge Q. E is equal to KQ R superscript 2. Work done in moving a test charge dQ through displacement dr. dW is equal to EdR. Therefore, potential difference. V is equal to EdR. Substitute E. V is equal to dr. Integration gives V is equal to KQR. Notice how beautifully the inverse square field produces a 1/r potential. Any field following inverse square law will yield similar form. Unlike electric field, potential is a scalar. Hence, V underscore net is equal to V plus V plus V plus. No direction, no decomposition, just pure addition. This is why potential problems are often easier than field problems. You do not struggle with components. This is the most important result. E is equal to V. In simpler words, electric field is the negative gradient of potential. Field always points from higher potential to lower potential. Potential decreases fastest in the direction of the field. For 1D situations, E is equal to dV dr. Whenever you feel confused about the direction of E, recall this. The field points in the direction where potential falls most rapidly. A surface on which electric potential is the same everywhere is called an equipotential surface. No work is required to move charge on an equipotential surface. Electric field is always perpendicular to equipotential surfaces. Two equipotentials can never intersect. Closer surfaces mean a larger electric field. For a two-point charge system, V is equal to KQR plus KQR. For a ring of charge, V is equal to KQ. For a disk of charge, V is equal to 2 pi k sigma. Field requires calculus. Potential only needs one integration. If charges Q and Q are separated by distance r, the potential energy U is equal to KQQR. For n charges, U is equal to sigma KQQR. Potential belongs to space. Potential energy belongs to the system. Students must never mix these two. The key result for work done in an external electric field is W is equal to Q. This is the true power of potential. Instead of dealing with forces, we handle energy. Confusing potential with potential energy is a common mistake. Other common G mistakes include forgetting sign conventions, forgetting that potential is a scalar, and misusing reference points. Also, assuming potential must be zero somewhere inside a conductor, or believing equipotential surfaces must be spheres are incorrect. G repeatedly asks about potential difference in uniform fields, potential inside-outside spherical shells, and work done from infinity. They also love questions on potential due to rings and disks on axis, and potential energy calculation for 3 charge systems. You'll notice something. G loves potential more than field, because potential is easier to test conceptually. In physics, potential is not merely a number. It is a measure of the stored possibility of interaction. Master this episode, and the next chapter, Gauss's law, will unfold with remarkable simplicity. Until next time, keep exploring.